Okay, hi guys. I thought I'd just make another video for a couple of reasons. First of all, to talk a bit about what's left on the spec to finish off, and also to talk a bit about the predicted grades. So you've probably had some emails. I think a letter was sent home telling you a bit about how the predicted grades are going to be calculated. Essentially, it's no great surprise. It's going to be based on things like your formal assessment marks, marks for homeworks, in-class tests, those sorts of things. So the time frame for that, I think, obviously it could change, but you should know your final grade around about the end of July. Bear in mind, obviously, what predicted grade I give you is potentially, open to being moderated up or down. Based on things like maybe your GCSE results. We're still waiting for clarification on that. So it definitely makes sense, I think, for all of you to try to finish off the specification. There's not a huge amount left. That then gives you the option, doesn't it, potentially of sitting an exam in the autumn if you want to do that. It may well be that you've got the option to sit the exam in the autumn and you keep the highest mark, either the grade that I give you, or maybe the grade you get in the exam in the autumn. If that's the case, it makes sense to have a go at the exam in the autumn. Again, we don't know the format, but it certainly makes sense to finish off the spec. Anyway, so well done to those of you who've been doing that. So what's left? So you should have finished forestry now. So one of the main topics left is air pollution. So air pollution divides into a few different categories. There's one practical, which we didn't get a chance to do, which I'll tell you about in a minute. And then apart from that, it really sort of splits into sort of acid rain and pollutants to do with smogs. So we'll talk about those in turn. So in terms of the practical is acid rain and seed germination experiment. Now in your textbook it's covered very well on page 250, sorry, completely wrong. It's covered very well in your textbook on page 416 to 417. So this is an experiment we would have done in class, where you have to sort of treat seeds with different acids at different pHs, and you measure the percentage germination to see if they affect germination rate. It's all pretty standard stuff. Things like standardizing your method, so same period of time. In terms of your plant seeds, making sure that you choose seeds that are genetically uniform, so the genetics of the seed doesn't affect the germination rate, things like that. Doing repeats so you get a more reliable mean, etc, etc. Anyway, it's covered very well on page 416, 417, so you could have a quick look at that and just write up that experiment so you know how that one would have been carried out. So next thing I wanted to talk about was acid rain. Again, so this is covered pretty well in the textbook. Hopefully you know already what the main pollutants would be for acid rain. Sulfur dioxide or sulfur trioxide, SO2 or SO3, and nitrous oxide. So it gets quite confusing with air pollution because some of these things might also be greenhouse gases. They may also be involved in smogs, so it gets a bit complicated. And in fact, one thing that would be very useful, I think, would be for you to go through the textbook, pick out each of the air pollutants, and for each air pollutant write down a source, an impact, and what the control measures are. I think that'd be a really useful thing. You could do that maybe as an A3 to the table. You could do it on revision cards, but that would definitely be useful. So the stuff on acid rain in your textbooks on page 250 through to 253, very top of 253. Main gases we've talked about. We did talk a bit about synergism before. Remember sulfur dioxide present with ozone. The ozone can oxidize sulfur dioxide to sulfur trioxide, and that produces a much stronger acid. So there's a little bit of that we have talked about before. In terms of the effects of acid rain, you can have impacts on abiotic factors, so non-living things, so things like corrosion of sort of metal railings, water pipes, those types of things, limestone buildings. That's fairly straightforward. Most of the stuff in the textbook is impacts on living organisms, and they split it into direct and indirect. So direct are kind of the things that you'd imagine, so things like leaf surfaces being damaged by the acidity, plant root hairs being damaged by the acidity, fish eggs, for example, crustaceans of sort of shells of crustaceans like crayfish being dissolved. They're all kind of direct ones. And then the indirect ones are really to do with how the acidity changes a feature of the environment. So one of the things with acid rain is in soils, for example, if you have acid rain running through the soil, it can often leach out some of the bases, so things like calcium and magnesium, so the soils become nutrient poor. If the soils are nutrient poor, then the plants may die from the lack of nutrients. So it's not directly to do with acidity, it's to do with how the acidity has affected the nutrients in the soil. There's other things as well, so those are covered quite well on page 251 in your textbook, so again you could have a kind of look through that. And then over the page 252 you've got some stuff about how you control acid rain, and there's a few different things. So some of these things might be, for example, removing the sulfur from fuels before they're burnt, things like coal desulfurization, and there's other things you can do maybe once you're actually burning things like coal in a power station. So you can do things like flue gas desulfurization, where you can spray in things like crushed limestone to absorb the sulfur. Again, they've covered quite well. So that's the acid rain stuff. Now what I will do is I'll send you some questions on all the stuff I'm going through now. You haven't got an air pollution resource booklet, so I'll have to kind of email you the paper and the mark scheme. So I'll do that and attach that with the email. So that's the sort of acid rain stuff. And then the next bit is to do with smogs. So smogs divide into two categories. So you have what are called particulate smogs. Particulates, fancy name basically for particles in the air. So particulate smogs are formed from incomplete combustion. So for example, if you have a bonfire, it's usually very smoky, and the reason it's very smoky is the combustion temperature is quite low. It's incomplete combustion. So anywhere where you've got a combustion not fully taking place, you get particulates, and particulates are in the news a lot, especially the very, very small particles, PM 2.5, which is 2.5 micrometers or smaller. They potentially can get into your bloodstream, and they could be linked with things like Alzheimer's, certain cancers, heart disease, things like that. So it's been in the news a lot, particulate pollution. There is actually some quite nice stuff on the Moodle site. I'm just going to log back in, get logged out here. So there's some quite nice stuff. There's a few articles and there's a few videos on the Moodle site to do with acid rain, particulate pollution, smogs, etc. So when you get a chance, have a look at the atmospheric pollution section. There's quite a nice video about Mongolia, very low air quality, and about smogs. There's also a really good link to the BBC website, So I Can Breathe. It's a kind of a section of the BBC website, but there's loads and loads of links to different types of air pollution affecting cities. Quite interesting, of course, at the moment with COVID-19, how the air quality globally is so much better. Historic lows, so it's only one of the few positives of COVID-19. So yeah, have a look on the Moodle site. There's some good stuff on acid rain. There's an acid rain PowerPoint. And then the smog section is really quite good. There's lots of videos, there's articles and links to different things. So particulate smogs, just come back to what I was saying before, particulate smogs are produced from incomplete combustion, and they have sort of specific impacts. I'll just try to find the section in the textbook here, which I now can't find, but it is in here somewhere. It has vanished. Well, here we go. So they call them smoke smogs, in fact, in the textbook. So page 245 onwards in your textbook, you can have a look through that, some of the effects they have on living organisms, affecting things like your chance of developing things like bronchitis, things like that. There's quite a nice section in the textbook about the very famous smog in London in 1952. It used to be called pea soupers because they were as thick as pea soup. So that's quite good. And then there's all the different sort of control measures for particulate smogs. So things like, for example, in a power station, having an electrostatic precipitator, having like an electrical charge that can attract the particles. So you have you positively charge the particles, and you have like negative plates, and they will stick to the plates. Things like cyclone separators, where you spin the smoke and the particles stick to the side, you can collect them. There's a whole range of different ones, etc. Diesel engines produce a lot of particulates, and they have particulate filters. Anyway, so that's covered pretty well, and that's pretty sort of straightforward. So the last bit in terms of smogs, the other category of smogs are what we call photochemical smogs. So photo, remember, means light. So this is where pollutants have reacted in sunlight and turned into, or chemical reactions have created another pollutant, for example, a secondary pollutant. So it's on page 248, 249 of your textbook. So, and it divides it into primary pollutants. So primary pollutants, remember, are things that are directly released into the environment by people. So things like nitrous oxide, for example, high temperature combustion, your car engine, your exhausts will contain nitrous oxide. That's a primary pollutant. However, primary pollutants can react in sunlight. There can be photolysis, photochemical reactions, and can form other pollutants. For example, NO2 can be split, or NO2 can be split into NO plus O. That single oxygen atom can join with O2 to make O3, tropospheric ozone. That would be a secondary pollutant. So it's quite a nice section talking a bit about primary pollutants and secondary pollutants. So the sort of cities that are affected by photochemical smogs tend to be ones that have a very sort of sunny climate for those photochemical reactions to happen. Places like Mexico City, places like Los Angeles are good examples you could quote. And then the sort of solutions to those things, I say, you can either try to remove the pollutants themselves. So for example, in a car engine, things like catalytic converters, which chemically reduce nitrous oxide back to nitrogen and oxygen. Or things like in a filling station, when you fill up your car with petrol, that the unburnt hydrocarbons, those can be collected, for example, vapor recovery. So it's all kind of covered fairly well in the textbook. So again, have a good read through that. Now, one of the important things about smogs in particular is the effects of features of the environment, and temperature inversions can often make smogs much more severe, can lead to sort of build-up of smogs. So I wanted to just talk a bit about what temperature inversions are. It is covered in the book. It's not that straightforward to get your head around. I'll give you the page numbers, and then I'm going to turn the camera around and try to draw a quick diagram to show you how these work. So it's on page 241 to 242. So when you get a chance, you could have a look at that. But I'm just going to turn the camera now. I've got a little whiteboard. I'll just try and draw out how these temperature inversions happen. So just bear with me a second. I'm going to try and do this all on one take to avoid me having to do any special editing, which will be a bit of a pain. Right. So let's just zoom in a little bit on that. Okay. Alright, so temperature inversions are common where we need certain climatic conditions. One of the things you need is very light winds. So they don't form everywhere, so they form often at night, and they form when there's very light winds and when you have clear skies. And they're very common where you have valleys. So for example, at night, so I'm going to put a little moon here so you know it's night time, with a cloudless sky, you get rapid heat loss. So as the ground gradually cools and the air above the ground cools, the air temperature drops, and of course cold air is more dense, so cold air tends to sink. So what you often find in valleys is at night you have cold air that will sink to the bottom of the valley. And so as that air cools and as it sinks to the bottom of the valley, quite often it reaches its dew point. So any moisture in that air will condense and form things like fog. So it's quite common, you often see this on the levels, you know, or in Taunton, that quite often you end up with sort of fog in the bottom of the valley, especially on a sort of winter's morning when it's been a cold night and there hasn't been any wind. And that's all to do with that cold air sinking to the bottom of the valley, condensing and forming sort of fog and things like that. Now, why does that matter? The reason it matters is that what you have to imagine the next morning, when the sun comes up, at the bottom of the valley, remember, you've got very cold air and you've got sort of fog and things like that. So when the sun comes up in the morning, that sun is able to heat up the valley sides. So the higher part of the valley warms up, so that the ground heats up, the ground radiates the heat to the air. So you end up with quite warm air higher up the valley, whereas at the bottom of the valley you've still got that cold air. The ground is maybe shaded by the fog and the mist, and if it's a very steep valley, it may be that the bottom of the valley is actually in the shade, especially in winter when the sun is low in the sky. Often the bottom of the valley may not get any sun at all day. So it's cold in the bottom and it's warmer higher up. That's why it's called a temperature inversion. It's the opposite of what the normal pattern would be. Now it matters in terms of pollutants, because what normally happens with pollutants is air pollutants are hot, Okay, if you think about the exhaust gases coming out of a power station, those exhaust gases are hot, and so they rise. They're hotter than the surrounding air, and that helps the pollutants to disperse. But if you think about a temperature inversion, if you had a power station, you had cars in the bottom of your valley, as that air rises, it cools rapidly in that cold air. So although initially the pollutants may sort of rise up, they're hotter than the surrounding cold air, they get cooled quite rapidly. And by the time they reach the sort of top of the cold air, they're actually cooler than the warmer air above. So because they're cooler than the warmer air above, they cannot rise and they can't disperse. And so the temperature inversion acts as a sort of lid. It stops the pollutants escaping and it stops the pollutants being dispersed. And that's really important because that can cause pollutants therefore to build up over a period of sort of maybe days or even sometimes weeks if the conditions are correct. That's sort of the kind of conditions you had in the smogs in London in 1952. You had very, very light winds, lots of cold nights, and the pollutants built up over many, many months. Temperature inversion is really important for stopping the dispersal of pollutants. So again, it's another feature of the environment that you could write about in an essay to do with how features of the environment affect the impact of pollutants. So hopefully that makes sort of reasonable sense. Right, I'm just going to zoom back and reposition the camera. Just bear with me a second. Alright, so that's features of the environment and how they affect pollutants. The other features of the environment you could also make a note of on air pollution is to do with acid rain and how features of the environment affect acid rain. There's a couple of ways you might better think of. One would be, for example, geology. So for example, you had acid rain but it was in an area of limestone geology, then that might help to neutralise the acidity. The other one you could have for acid rain that's important is wind direction. So it's quite common in the past for the sort of sulphur dioxide produced in UK power stations to be blown by prevailing southwesterly winds to places like Scandinavia, Norway and places like that. So wind direction is very important at affecting where acid rain travels. Acid rain is particularly damaging to trees, to pine trees, again in plants. You can make a note from the textbook on that. And also it can affect lakes and rivers and things like that. So those are some of the features of the environment that affect acid rain as well. And that's basically it really. That is all of the air pollution module. Obviously if we were in college that would probably take about 4 or 5 weeks to go through. It's one of the last big topics. So I definitely recommend you doing that work, and I'll email you some past paper questions to have a go at as well. I don't think it will take a huge amount of time. It's probably 3 to 4 hours work maybe in total, something like that. And then after that, all you've got left is a little bit of stuff on radiation and a little bit of stuff about waste disposal, things like landfill and incineration. And I'll set you that maybe in perhaps 10 days' time, and then you're done. And that's the end of the specification. So I think it's worth doing it and sending me the work for me to check, because then if you want to sit the exam in the autumn, if it's available, you've got the option of doing that. So well worth doing. Alright guys, hope everyone's well and stay safe, etc. and all the best. Cheers.